using the two methods, protein abundance-based and pairwise ratio-based. It's now time for you to take a break, and the rest of us will carry on. What we have here is the two methods, which obviously is great. You have choice. But on the other hand, it's again one of those questions which arise: which method to use, which one is better for my experiment. And I hope that after some discussion here, you will be able to choose the correct one. The protein abundance-based methods, and it is similar to the discussion we have about normalization, those will be very sensitive when it comes to missing values or outliers. So we would recommend to use protein abundance-based protein ratio calculation for TMT type of data, especially TMT based on MS3 quantitation data stream. But we would recommend pairwise ratio-based method for label-free quantitation. How these individual methods handle the sample groups, replicates, is shown on a hypothetical numerical example. We have here the two conditions, placebo and drug treatment. We have a group of mice subjected to placebo and a different group of different mice subjected to the drug treatment, and we have 3 peptides detected from a particular protein of interest. And you use a summed protein abundance approach. The software adds together the contributions of individual peptides and gives you a value representing the protein abundance. Straightforward. It does it for the mouse 2, and mouse 3, etc., etc. Then from each of the groups of the sample, in this case, I have 3 samples in the placebo group, it selects the median. In our case, it is the value 105, and that will then represent the placebo-treated mice. It does a same selection of median from the drug-treated samples, and then finally calculates the protein ratio. A very straightforward method, easy to follow and understand. Where the problem lies is the missing values, because obviously with the values being based on the summing of contributions, if you have some missing values or major outliers, this could impact the final outcome in a considerable way. So that's why we would recommend for label-free quantitation in particular to use the other method, the pairwise ratio-based protein ratio calculation method, where we do a lot of so-called pairwise ratios being calculated in the background. Those are not shown in any of the results tables. And then the software will select a median of this population to represent the entire the protein ratio. So what we do here numerically in the background is that we take and first divide for each of the peptide the value we found for mouse 4 with the value we found in mouse 1. So you get a column M4 divided by M1, and you have 3 values because we have 3 different peptides. Then you move on to the other combination, mouse 4 divided by mouse 2, and again you get 3 values for each of the peptides. In this case we have no missing values, everything is running nicely, and then you repeat that procedure for the M4 divided by mouse 3. Then you move on to the next mouse in the drug treated group, M5, and divided by M1, M2, and M3. And you get another 9 values here, 3 columns. And the last repetition for the mouse 6 from the drug-treated group divided by mouse 1, 2, and 3 from the control group, placebo. Then you have a population of 27 values pairwise ratios, and you select the median, and that median will then represent the protein ratio. This is a very robust method because here, considering again the two missing values we had previously, we see that they have practically no or minimum effect on the final protein ratio outcome. So that's why I would say this is a method to use. We can compare the two methods against each other, and in addition to the benefit which I already mentioned with respect to the missing value treatment, uh, we have some other um, things to consider. For instance, the use of a or selection of a hypothesis test, because certain protein, you know, ratio calculation methods much better a particular hypothesis test. We have two hypothesis tests in PD. We have ANOVA and t-test background based, and as you see, they are allocated such that if you have used protein abundance based protein ratio calculation method, you should we recommend you use ANOVA for your validation of the ratio changes, while if you use pairwise ratio based method for protein ratio calculation, you should be using the t-test background based hypothesis test. But there is one limitation of the t-test background-based hypothesis test, and that is that it relies on a background. And the background are basically a big population of proteins which are not changing between sample condition A versus B. And if you don't have such a background, then if the background is too small, any evaluation will be not valid. That's why we programmed in a hardcore cutoff. We require that for t-test background-based hypothesis test to be run, to even start running, you have to have at least 500 items in the list, whether it's proteins or peptides. Normally, there is no problem with getting 500 peptides identified, but in some samples, it is already a bit of a challenge to get at least 500 proteins detected in both sample groups you are comparing. So that is the only thing you should have in mind. In that case, you would have to, give up on pairwise ratio based calculation of protein ratio connected to t-test and move on to the protein abundance based with ANOVA instead. Just again, one of those nice plots showing technical mixtures. This is a mixture of 3 proteomes in different concentrations. We use this kind of samples very often, and maybe it's something you might consider for your benchmarking as well. What is the sample is the same amount of human protein home digest. Those are the blue points here, put in 2 samples in the same amount, so that's why they should cluster around the ratio change equals 0, log 2 ratio change equals 0, and then there is a different spiked amounts of E. coli and yeast digest as well. Those are the 2 populations in red on the left and right from the human non-changing population. And what we are looking at in these plots is again the shape of these different color distributions and their spread, their width in a way, if you want. And what we see that with the protein abundance based method, whether it's based on some abundance or the top 3 method, we see these distributions are quite spread out. And the situation is significantly improved if we use pairwise ratio method. Obviously, this was a labor-free quantitation. Okay, so this just shows that pairwise ratio protein ratio calculation methods has definite benefits. It handles better the data with the missing values and gives you a better outcome, better results.
Leaves of a plant.
the same plots in different colors. Now, what I'm trying to compare is different protein ratio calculations here. What I am looking again at the shape and the width of the distributions and any particular irregularities. And what I see in this case that this pairwise ratio is actually improving the results, even with the top 3 method where we were not that happy. We looked at this plot earlier when we used protein abundance based approach. With the pairwise ratio, the same data are giving basically much improved appearance. But it all works very nicely in combination with the sample replicate estimation calculation of the peptide or protein abundance, and that's what's shown on the last picture here at the bottom right. So these plots are really useful. I hope you become familiar with them and you can then use them yourself. Okay, so there is also a parameter for data imputation mode. We have 2 different modes of data imputation. And I would just mention that if you decide to rely on sample replicate estimation doing the imputation in an automatic fashion, do not select any imputation mode here. Basically leave it at imputation mode equals none. For those of you who, for some reason, are not going to use the sample replicate estimation approach and would like to have
also forms part of Mother Earth.
done on your samples.
So we take up the responsibility of becoming human beings. And this responsibility of being
and that they are available for practically all of the quantifier node, except that the reporter ions quantifier is having only one method allowed there, and you just let the software to run through. Imputation has all sort of limits set up so that we do not introduce some significance which was not there before the imputation was done. And there are also randomly generated value within certain tolerances, and always in the final results you have a way to see whether the value you are looking at is the detected one or the imputed one by looking onto the abundance origin column of the proteins and peptides groups page. Mm-hmm. So no more about imputation. It's not a popular thing among our software developers. And as I said, the new sampler replicate estimation method is for protein abundance calculation is taking care of some of this problem of missing values by some automatic imputation there. And we now move on to the hypothesis test. And again, it is a topic I have discussed earlier. I hope we will go through that quite quickly. Hypothesis test is a way of obtaining p-values. P-values should tell you how likely, what is the significance of the change in ratio in your samples. And it always is set up that way that the lower p-values are the ones you are interested in, while the higher p-values are the ones confirming no significant difference. What cutoff thresholds you set is your particular choice. Most of the people decide to use cutoff 0.05, but as always with these parameters, it is your choice which you have to justify. I mentioned the two methods we have, the ANOVA applicable to both nested and non-nested experiments. What I would say about ANOVA is that if you want to use it, you use it with protein abundances. So the method you select for protein abundance calculation is important. You remember that missing values would be an issue. And for ANOVA, we would recommend you would have at least five technical, five replicas or five samples in each sample groups. It is because the labor-free quantitation data are data with quite a high variation in it. And if you look at the little plot which I pulled out from the Ishai Levin's publication on the bottom right there of the screen, and you can see that depending on the certain variation of the data, of your quantitation data you admit for the in your final result evaluation, you will have to have a certain number of replicas. And below that, it would not simply be possible to consider certain fold change significant. So let's have a look at that plot again. Here at the bottom, you have a fold change, and most people would decide that fold change equals 2 would be something they would consider significant. But then you have to look at overall variation of your data, and those are the curves which are plotted in that graph. Let's consider variation of 50%. Then reading from the plot, going from the fold change 2, reaching to the 50%, dashed line there, but you can read that you would need at least about 5 replicas per sample group. So this is what we would recommend as well for the ratio change 2 to be considered significant. If your data are having much higher variation, you can read from that graph very easily how many more technical replicas in the sample group you would have to have in order for two-fold change to be statistically significant. The numbers get quite staggeringly high very quickly. If you decide, on the other hand, or if you have very nice data, high quality, low overall variation, you see that, for instance, with 5 sample replicas reading from the y-axis, you can say that with 5 sample replicas and the overall variation of up to 25%, you might actually already see or consider a fold change ratios 1.5 to be statistically significant. So I would recommend to look at this small publication. It's just a couple of pages, and it might help you when you are setting up your experiment. At the bottom line, if you work with ANOVA, number of replicas is very important, and we would recommend, based on our experience for proteomic experiments, at least 5 in each sample groups. And this is not what everybody has. And for that reason, we would then guide you to use the background t-test. Why? Because it, strictly speaking, doesn't need any replicas, and you can just compare sample A versus sample B with having basically just one file, one sample in each of these A and B groups. But there are certain assumptions. One of them is that most of the proteins between the two samples should not be changing. That comes from the idea that we need to have some stable background in the population. And the second assumption, which is confirmed and detailed in the publication cited at the bottom of the slide, is that the variable, well, it's an assumption and then verified, that verified in the nature of the data, that variability of the proteins of similar abundance is the same. And that's important because what I will be showing you now, how this background method is working. Again, using the scatter plot. In this case, abundance ratio log2 at the the x-axis, and some abundance surrogate on the y-axis. It could be abundance, or it could be abundance ratio weights. That would not make much of a difference. So here we have the plot of our technical experiment. There we don't expect any changes, more or less. It was an experiment, same sample injected twice, and plotting then the ratios against the abundance look like this. Now what we can do, or what the software is doing in the background, it slices this distribution into subpopulations based on the abundance of the protein. So we have a small population on the top, which are very abundant proteins. They will usually have a very low confidence interval. They will be very tight, very reliable data. But the lower you go in abundance, the poorer the quality of the data is. The higher the confidence interval will have to be um, uh, when we are then calculating the statistical significance. So this stratification of the population is important because when you then decide that you want to check whether the particular protein is changing significantly between the two samples, the software will go into the subpopulation of those proteins which are of similar abundance to the protein you are asking about, and will then calculate their confidence interval, which is using a special calculation method. We call it robust standard deviation calculation. You can, if you have interest, again refer to the publications I have mentioned. Within this confidence interval, we make use of the second assumption that our protein of interest have the same confidence interval, and then we can check whether the ratio change considering such a confidence interval is statistically significant. So let's say in this case it is statistically significant, and we can proclaim our protein changing in a statistically significant manner. Let's now have a protein which is showing the same ratio change. It is more or less at the same, on the x-axis, the same value, but it is one of the low abundant proteins. There, the population it is being compared to, the background is a different bunch of proteins. Their confidence interval is much wider, and it can be shown that with such a wide confidence interval, this ratio, which for a higher abundant protein would be significant, is significant not anymore. And then we can have, of course, the third case example. A protein is changing far less than our red protein did in the beginning, but because it is belonging to the population of high abundant proteins where confidence interval is very narrow, even this smaller change would be proclaimed statistically significant. So what we are getting here is this sort of lines of defined confidence interval, which you can then color in proteome discovery with this color scale, giving you a visual representation of significant or non-significant changes in your population. So I said that this t-test background based has this benefit that it works with even just one sample per group. It is not the ideal situation. You obviously want more samples because it will narrow considerably the confidence interval and improve your chance of detecting even smaller ratio changes considering statistically significance. So definitely do not work with the minimum number of samples you have, like 1 versus 1, but try to get more replicas if possible. Comparing the two tests, they obviously work with the same ratio values. And then we have two different plots, two different appearance appearance of the plots they produce. ANOVA gives this typical volcano plot, while the background t-test is giving a bit strange, a lot of people consider it strange, um, plot looking like a parabola. It's showing you basically a distance function from the background. This parabola shape will appear when the number of your background values is quite limited and there is only one population. Maybe you have just above those 500 proteins, which is an absolute minimum. In the real life, where you have more proteins identified, the volcano plot from the t-test background-based method should look a bit more like this, where you have more or less many overlaid parabolas, because you can divide your proteins into different subpopulations based on abundances, and it then acquires appearance like that. Then what I have here, a couple of slides on different watching or studying what effect a different protein ratio calculation would have if you are using the background t-test hypothesis test. Here I have one of those technical mixtures I have been showing earlier. It is a sample, basically dilution, same sample ratio, 2 to 1. What we should basically see here is the minimum number of up and down regulated proteins. If we center that area or center that population at the log2 ratios 1, and that's we have just couple more or less detected, either with stop 3 or the sample replicate estimation method. Let me see. When we then use the peptide pairwise ratio based method for protein ratio calculation, we see that there is a slight improvement compared to protein abundance based protein ratio calculation, simply based on that the number of up and down regulated points, data points, is smaller. So this is just one of those validation slides which you might produce in Proteome Discover and check. And this is the same thing, looking again at protein ratio calculation effect on the when we are using the background t-test, and looks very similar to the plots I have shown you earlier. Again, we would recommend using pairwise ratio, and we would recommend the sample replicate estimation method as well. So, compounding synergistic effect of both methods, improving your final outcome. Now, I believe we are now at the end of the presentations, and even though I have a couple of slides, we haven't really missed much. Finally, I would just simply mention the table comparing the hypothesis test benefits and perhaps some limitations. You already heard about the minimum of 500 items being detected in order for the t-test background-based method to run. And with that, I would end the presentation today. The last few slides which you have included is just reminding you that we have other statistical methods built into Proteome Discover. There is a PCA, there is a heat map, and there is perhaps what you should not forget, the statistic insights node, which we introduced in the version 3.3, where we have options of calculating all sorts of reasonable statistics and meaningful statistics, where we would hopefully make your life easier. There has been a separate session on the statistics insights node I presented last year together with with my colleague Pedro Navarro, and I would recommend those of you who are interested to go and look at this past recording and start using this node, as it is quite useful. As you see here, a lot of calculations can be done in the background, presenting you with the results. With that, I would like to thank you very much for your patience, for your questions. There are many coming in, so many that I don't think we will be able to go through any of them now. Please keep questions coming. Use the pd.support address, and we definitely, together with my colleagues, reply to those. And those questions submitted today in the session, as I said, I will work through them. And within a couple of days, you should be able to find the answers directly in the as a document added to the materials of the session. Plus, those of you who submitted questions, they will receive direct answer from me directly to your email address from the pd.support. So that will be taken care of that way. With that, once again, thank you very much, everybody. It was a big topic. Just a preview for next. In 2 weeks, on the February 24th, we will be having another quantification session, this time on processing targeted quantitation hybrid DIA data from instruments like Astral. Those of you, but not only Astral, whenever you have a possibility to acquire now on modern systems, you Exploris, Exedian, and Astral, hybrid type of data, combining targeted quantitation and generic data independent acquisition in one raw file. You will require specific software, and at present, I believe it's only Proton Discoverer which can process such data files in one go and giving you the results from both types of data in the same report. So that is coming on February the 24th. If that is your cup of tea, please register, and we will see you there.